Keep on hustling. Can't stop, gotta claim what's mine.
Hello and welcome to the video on the gradient and directional derivatives. So to start, we'll go over what is a gradient. So gradient is denoted by the symbol, it's like an upside down delta, upside down triangle thing. It just means gradient, the symbol for the gradient operator. So the gradient of f at p is basically a vector. So this is a vector thing whose components are the partial derivatives, which we've learned how to do. So are the partial derivatives of some function f that we have, and at a point p, which could equal a, b, or even a c. Okay. All right. So basically, in two variables, this is what it would look like: is the gradient at f of p, or gradient of f at p, is equal to the partial derivative of x with respect to x evaluated at a, b, and then comma. So that was the x component, and the y component is the partial derivative with respect to y evaluated at a, b. Okay, and a, b is our p point. Okay, and then in three variables, it would look a little bit different. Instead, we're going to have three components. Okay, so we're going to have an x component, a y component, and z component, and they're each respectively the partial derivatives with respect to those variables. And instead of plugging in just AB, we're going to plug in ABC because it's three variables. So then for our y component, we have f sub y at A, B, C. And then for our z component, we have f sub z at A, B, and C. Okay, so that's basically it. That's all you do for a gradient. And sometimes, just to note, so sometimes it's written in Leibniz notation, which would just be the following. So then we would have gradient, sorry, that was a really bad triangle. Okay, gradient of f at p is equal to the partial derivative, and then we have a, b, c, and then partial with respect to y of a, b, c, and then partial with respect to z of a, b, c. So anytime you see some kind of d or like fancy d or stuff like that, that would be Leibniz notation. That's what it's called. Okay? Alright, so now let's go over some properties of the gradient. So properties of the gradient. Okay, so the first property, like a lot of things, well, before we start with properties, we're going to assume, so if f of x, y, z, if this multivariable function, and g of x, y, z, another multivariable function, are differentiable, and c is a constant, so these are the conditions, constant, then we have that, we can actually deduce or conclude four things. So one is that the gradient of f plus g, those functions together, it is equal to the gradient of f plus the gradient of g. Okay, so that's one of the properties. That would be like the sum rule, equivalent to the sum rule. Another thing that we have is the constant multiple rule, where if we have that constant c multiplied times our function f, we could basically just pull that c out and calculate the gradient of f and then multiply the c at the end. Okay, so that's the constant multiple rule. And number three would be if we had if we're multiplying the two functions together and then taking the gradient, this is we're going to implement the product rule. So this is called the product rule for gradients. And it basically works the same way as the product rule for differentiation, except for saying uv prime instead of uv prime plus u prime v. Instead of differentiating once, we're going to have that differentiation be the gradient operator. So, for example, we would write the first function by itself. Okay, so that just stays the same. And then the second one, we would take the gradient of it. Okay, we would compute the gradient, and then we would add that to add to that the gradient of f, gradient of the first one, times our normal g. Okay, so this is the product rule for gradients. And the last property, I'll write on the next slide. So this is going to be called the chain rule. So this is number 4. This is called the chain rule for gradients. For gradients. Okay, so let's say if f, capital F of t is a differentiable function, a differentiable single variable function. Okay, so you only plug one thing into it and you get out something, right? So single variable, then we have that the gradient of capital F of our multivariable function. Okay, so the gradient of that is basically going to be, we're going to differentiate the outer function. This is the outer function, that's capital F, and this is the inner function, so that's the inner. Alright, so we're going to differentiate the first one, so we just have f prime of, we'll keep the inside the same. And then we're going to differentiate the inside, but in this sense, since we had that gradient operator out here, we're gonna, when we differentiate it, we actually write the gradient of it. Okay, so gradient of f. Okay, so in another sense, so gradient of f, right? So this is gonna be kind of like, well, we'll do an example of it, but another way to rewrite it is just f prime of whatever's on the inside to begin with, right? And then we take the gradient of the inside, so that'll be basically like something times something here times the gradient, which would be f sub x, f sub y, and f sub z. Okay, so let's do an example of this last one. It can get a little bit tricky just to begin with, so we'll start with that. So what we're going to do is find, so we're going to find the gradient of f of x, y, z, which is equal, well, I'll actually use a different variable here. So we'll just say, let's say this is something like, let's think of a letter, like k of x, y, z. So some function of 3 variables is equal to x squared plus y squared plus z squared, and this is quantity raised to the 7th power. So here we see an outer function, right, this raised to the 7th power, and an inner function of just x, y, z. So we could actually split this guy up into 2 different functions. The outer function is going to be given by, I'll say f of, and we'll just use a t to replace the x, y, z stuff. So t to the 7th, that would be our outer function because we're saying that something is being raised to the 7th power. Okay, and then that inside t, that becomes, this is our f of x, y, z, our lowercase one. That's our multivariable function, which is the inner function, which is x squared plus y squared plus z squared, right? So this is the inner one, inner, and this is the outer one, outer, where t is equal to this whole thing in here, okay? Likewise, I could have written capital F of lowercase f is equal to f to the 7th. You could just use any variable, I just didn't want to get it too confusing in there. Okay, so what we're going to do to find the gradient of k, right, so that's going to be basically the gradient of f of x, y, z, which, according to the chain rule, is equal to f prime of f of x, y, z times the gradient of lowercase f. Okay, so let's continue this on the next slide. I'll write everything, I'll copy everything down there. So our original function was x squared plus y squared plus z squared to the 7th. We know that f of, I'll just write an f here, is equal to f to the 7th. And then our f of x, y, z is then x squared plus y squared plus z squared. Okay, so let's start with where we left off. So we had that the gradient of capital F of x, y, z, let's see, we got 3 parentheses going on there, okay, is equal to capital F prime of f of x, y, z, sorry, it's kind of long here, the process, and then the gradient of f is going to be equal to f sub x, f sub y, and f sub z, okay? So here, we're going to have, let's compute this, so f prime is equal to, that's going to be basically 7, you bring down the 7, this is the power rule, right, so 7f to the 6th, so we can write that 7f to the 6th, and this f is basically this thing, right? So we'll replace those x, y's, and z's in at the end, toward the end. And then we have that multiplied times f sub x, so the partial derivative of this function here with respect to x, so that's just going to be a 2x because the y's and z's go away because those are considered constants, right? When we're looking at with respect to x. The next term would be a 2y, and the last component would be a 2z, okay? So it's kind of some symmetry going on there. Alright, so now what we have to do, we can replace this f here with x, y's, and z's. So we have 7 times, and f is x squared plus y squared plus z squared, and then to the 6th power. And what we can do with this vector is actually factor out a 2, right? We can take that 2 out, so we'll take a 2 there. And then we have x, y, and z in there. So our final answer could be 7 times 2 is a 14. We'll combine those. Then we have x squared plus y squared plus z squared raised to the 6th power, and then times the vector x, y, z. Okay, so that's basically the gradient of our given function.
In a minute, they'll be trying to pump a gauge in me. Leader of the G committee, Funkadelic, better tell it to the fellas I ain't the one to be played with. If you think you gonna be